welcome to this explainer. Let's just jump right into an absolutely fascinating chapter in the history of artificial intelligence. We're going to explore the very first major commercially successful paradigm in the field, expert systems. It's a story of a profound technological breakthrough, but it's also an intellectual cautionary tale about how we actually understand human reasoning itself. In the knowledge lies the power. That quote brilliantly illustrates exactly where our story begins. It's a simple yet totally revolutionary principle coined by computer scientist Edward Feigenbaum, and it fundamentally shifted AI research in the late 1960s. Instead of trying to build these general, universal reasoning engines, researchers pivoted toward highly specialized, deeply knowledgeable systems. But to understand why that shift was so massive, we have to look at what they were trying to do before it. Section 1. The limits of general search. Going into the 1960s, during the first decade of AI research, the prevailing idea of problem-solving was essentially a general-purpose search mechanism. Researchers were trying to build universal problem solvers, literally programs that could just string together basic reasoning steps to find complete solutions for, well, just about anything. But very quickly, they hit a massive wall. Notice the stark contrast here between weak and strong methods. Early researchers relied heavily on what they called weak methods. These were general-purpose search strategies. Sure, they were broadly applicable, but they simply did not scale up to large or difficult real-world problems. I mean, even with just a few dozen facts, a computer's computational resources would be entirely exhausted. The alternative? Strong methods. These relied on powerful, domain-specific knowledge that allowed for much larger, highly efficient reasoning steps in really narrow areas of expertise. Section 2. Knowledge is power. This realization led to a huge paradigm shift at Stanford University. Researchers suddenly realized that general reasoning algorithms weren't the secret to intelligence. Information was. The big breakthrough came in the form of a program called DENDRAL, developed at Stanford by Ed Feigenbaum, Bruce Buchanan, Nobel laureate geneticist Joshua Lederberg, and a prominent chemist named Carl Djerassi. DENDRAL was given a very specific and extremely difficult problem. It had to infer organic molecular structures from data provided by a mass spectrometer. DENDRAL was the very first truly successful knowledge-intensive system. It didn't try to be a general thinker. Instead, it relied on a massive database of incredibly specific chemical rules. Okay, let's dive into this, because this is how DENDRAL actually worked. It essentially replicated human expertise by relying on heuristics. Now, heuristic is basically a rule of thumb, or what mathematician George Polya famously called the art of good guessing. You see, as molecules get more complex, the number of possible structural combinations just skyrockets. Heuristics allowed the system to quickly prune that massive search space by immediately throwing out the highly unlikely or irrelevant solutions, exactly like a master chemist would do intuitively. And this brings us right back to our core principle. DENDRAL's success completely proved the knowledge is power hypothesis. The system's true strength didn't come from some clever new algorithm or brilliant underlying code. No, it came from the sheer volume and quality of Dr. Djerassi's expert chemical knowledge that was programmed directly into it. As the researchers themselves noted, to solve a hard problem, you really have to almost know the answer already. Section 3, Anatomy of an Expert System. Moving into the 1970s, this whole concept evolved into a formal architecture. Researchers realized that, hey, if we can replicate the success of DENDRAL in chemistry, we could theoretically build expert systems for nearly any complex professional domain out there. But to do that, they needed a structured way to actually build them. This birthed an entirely new discipline called knowledge engineering. Think of it as a highly specialized form of mining. Knowledge engineers literally had to sit down with human experts, doctors, scientists, engineers, and meticulously extract these precious, unwritten rules of good practice right out of their minds. They had to take that fluid, intuitive human judgment and somehow formalize it into rigid, hard logic that a computer program could perfectly execute. Let's look at how this builds into an actual software architecture. The diagram here illustrates the era's elegant breakthrough. Notice the really clean separation. At the bottom, you have the knowledge base. That's the static store of facts and heuristics, your if-then rules. And distinctly separate from that is the inference engine, which is the active mechanism that processes those rules. This modular design was absolutely brilliant because it meant you could literally swap out the knowledge base for a completely different subject, all while keeping the exact same underlying reasoning engine. A true game changer. Section 4, Reasoning with Uncertainty.
That modularity led directly to the next major frontier, which was medicine. Feigenbaum and Buchanan teamed up with Dr. Edward Shortliff to build a system called MYCIN, which was designed to diagnose severe blood infections and meningitis. But medicine presented a really unique challenge that chemistry just didn't have: biological uncertainty.
Remarkably, MYCIN was able to perform at the level of an actual infectious disease specialist, and considerably better than junior doctors. And get this, it did all of that using a knowledge base of roughly 450 rules. Just 450. It acquired this incredible expertise through extensive, painstaking interviews with specialists who basically passed down the exact diagnostic guidelines they were using in their daily clinical practice.
So, the really crucial point is how MYCIN arrived at a diagnosis using those 450 rules. It used a goal-directed control strategy known as backward chaining. Let's follow this logic map together. The system starts with a goal, say identifying the organism causing the infection. Let's call that C. It works backward, looking for a rule that concludes C. It finds rule 1, if B, then C. Now, B becomes the new goal. It looks for a rule to establish B, finding rule 2, if A, then B. Finally, it hits a point where it just needs raw data, so it asks the physician, is A true? It's a really elegant chain of deduction that works entirely backwards from the hypothesis straight to the evidence.
But again, medical evidence is rarely absolute, right? To handle this, MYCIN incorporated a calculus of inexact reasoning using what they called certainty factors. For example, a rule might say if the organism is a rod and the patient is a compromised host, then there is suggestive evidence, let's say a certainty factor of 0.6, that it is Pseudomonas. This wasn't strict probability, it was a clever way to track a physician's shifting strength of belief as new, highly imperfect evidence was gathered in real time.
Section 5. The Knowledge Acquisition Bottleneck. Now, MYCIN was incredibly influential. By the mid-1980s, the tech industry was in an absolute frenzy, building expert systems for everything from mineral exploration to computer configuration. But the excitement wouldn't last. Let's look critically at the structural hurdles that caused this entire paradigm to plateau, starting with its most fatal flaw.
Remember that mining process of knowledge engineering we talked about earlier? Well, it turned out to be a massive problem. Building these systems was essentially a cottage industry. It required highly specialized computer scientists to sit for months, sometimes even years, with individual human experts, painstakingly handcrafting and testing every single rule. This became known in the field as the knowledge acquisition bottleneck. It was incredibly tedious, slow, and hugely expensive. Even Edward Feigenbaum himself recognized that this manual, artisanal process of transferring human expertise into rigid computer representation was simply too slow to ever scale up to general intelligence. The systems were incredibly powerful within their tight boundaries for sure, but expanding those boundaries was just agonizingly slow.
Section 6. The Fall of Symbolic AI. The bottleneck was really just the beginning of the end. As these systems were actually deployed into the messy real world, the architectural limitations of using rigid symbolic logic to capture fluid human reality became painfully obvious, and that directly led to the collapse of the era's excitement. The fatal flaws basically compounded on one another. First up was rule explosion. If a system needed thousands of rules to operate, the way those rules unexpectedly interacted with one another became an absolute nightmare. And this led directly to the second flaw, maintenance complexity. Think about it. If medical guidelines changed, finding and safely updating the exact interacting rules without breaking the whole entire system was incredibly difficult. And third, perhaps worst of all, they completely lacked common sense. This severe lack of common sense manifested as brittleness. Expert systems operated perfectly while standing on a narrow, high plateau of specialized knowledge. They were absolutely brilliant within their specific domain, but the moment they encountered a problem or a piece of data just slightly outside their programmed rules, they didn't degrade gracefully like a human would. No, they fell off the precipice entirely, failing precipitously to levels of utter incompetence. Yet, honestly, it would be a huge mistake to view this era simply as a failure. It was actually a deeply revealing moment in the history of computer science. As researcher Eric Horvitz noted, the expert system zeitgeist pioneered the entire concept of AI as a tool to augment rather than replace human reasoning. It taught us that capturing human expertise is incredibly valuable, even if perfectly replicating human flexibility is way harder than we initially thought. Ultimately, the field had to adapt.
To handle the messy, uncodifiable uncertainty of the real world, the things we just can't easily write down as simple if-then rules, researchers were forced to abandon rigid symbolic systems. Instead, they shifted heavily toward probabilistic methods, like Bayesian networks and machine learning, which could actually learn from data rather than relying entirely on handcrafted human rules.
The story of expert systems leaves us with a truly profound question about the nature of intelligence itself. They proved beyond a shadow of a doubt that specialized knowledge is incredibly powerful. But can the nuanced, fluid art of good guessing, inherent in true human intuition, ever truly be captured by rigid symbolic logic? Or will there always be a part of human expertise that remains uniquely, unprogrammably ours? It's definitely something to think about as you consider how we interact with the complex systems around us today.